So, of course, lots of types of data can be represented as networks or graphs where you've got a set of nodes that correspond to individual people, and edges in the graphs, possibly augmented with additional information, that represent relationships between people and information about those relationships. So, you know, the classic example we tell all our algorithm students about is the Facebook graph. You know, graphs from various kinds of social networks came up in Vitali's talk, but we might also be interested in like telephone call graphs or you know, students who take classes together, or you know, whatever it is. There are lots of different types of data we would want to represent this way. Okay, so you know, right, Facebook graph, and of course these graphs contain lots of potentially sensitive information. And because of that, people have tried to publish information about graphs using various kinds of anonymization, and as we found out in Vitali's lecture the other morning, this generally doesn't work very well. You know, there are de-anonymization attacks on various kinds of network data, both social networks and also data about sort of computer networks, computer network topology, and so we're in this situation where straightforward attempts at anonymization have generally failed, and so or either failed or just completely destroyed any useful information about the graph. And so we're left in this situation where we don't really have a good way of communicating information about the data set we have without like basically revealing the data set. So, so this is going to be the theme for the talk. What kinds of things can we do? What kinds of techniques can we use? All right, so we're going to be looking at differential privacy, as you might imagine, given the theme of the workshop. And for graphs, it's worth pointing out that there are like at least two definitions of what privacy might mean, right? So two natural definitions. In fact, there are many definitions, and I'll say a bit more about that in a second. One of them, the first one you might think of is sort of edge differential privacy, where we say two graphs are neighbors if they differ in the addition or removal of a single edge in the graph. So like in these two graphs, they're almost the same, except there's this like extra connection between the blue and the little red person. Okay, and in node differential privacy, it's a sort of a stronger notion of privacy. So we're going to allow like a more sort of a more powerful metric, larger set of adjacent graphs. So we say two graphs are neighbors if one can be obtained from the other by deleting a node and all of its adjacent edges. Okay. So we make, and the flip side to that is that you could also go from G to G prime by inserting a node and an arbitrary set of edges along with that node. And just sort of jumping ahead, this stronger notion is going to be harder to achieve because you have to hide more information, and because adding one well-connected vertex can actually drastically change a lot of the quantities we think of as sort of basic descriptive graph statistics. And we'll see examples of that. Okay. So I'm going to focus today on node differential privacy because it's the stronger of these two notions, and it sort of, I feel it best captures the intuition we have that we want to hide the presence or absence of an individual from, or the use of an individual's data in the computation. And here, the sort of data about an individual consists of that person and, of course, all the relationships they have. Right? It's not that just one relationship is a problem. We're really interested in sort of the complete picture we have about that person. Nevertheless, because edge differential privacy is simpler and easier to achieve, there's a lot of work on it. You can read these citations some other time. And there's sort of another notion called node zero knowledge privacy that came up in a paper of Gerke, Liu, and Pass. And this is sort of actually more closely to related what I'm talking about today, but I'm going to sort of I'm going to skip over it just because it makes additional assumptions about it makes assumptions for privacy about the structure of the graph, and we're going to try and avoid that. Okay. So the basic question for this talk is going to be what graph statistics can we compute subject to no differential privacy? Now, something I meant to add a slide about, and I forgot to, is just sort of thinking about this definition a little bit. So one of the things that what I said a second ago is no differential privacy hides the use of all the data we have about a particular person. Okay, so that's their data and all the data of the edges that are connected to them. Now, it's sort of, one would often want to interpret that as saying it hides the presence or absence, or like the participation or non-participation of any particular person in the data set. And in the case of network data, that may or may not be true, and it sort of has to do with the way network data is generated. Okay. So just to give you an example, so one way to think about it is that somewhere out there, there's some sort of big population, which is some huge graph, the actual, let's say, the graph of all people in the world and all their relationships among them. And then what we're getting is some subgraph of this graph. What our data set is some subgraph of this graph, maybe like a random subsample of this graph or something like that. Okay? And so then, when I sort of insert or remove one person from this data set, it sort of semantically it still makes sense. Okay? On the other hand, we can think of a sort of like a different model for how this data would be obtained, which is where, so for example, and I was talking to sort of someone who basically does this kind of thing. For example, suppose I'm running a study on some population that's generally hard to reach. We might be looking at, in the example I had of this person I was talking to, like heroin addicts in the Boston area. Okay? So it is like difficult to go out and take a random sample of people struggling with heroin addiction because they're not necessarily easy to find. They don't necessarily like advertise their their problem in some public way, and they don't even necessarily have like a medical record of this issue, right? Because they may not be something that they're dealing with via the medical system. And so the way that these studies are done is you find one such person, the researcher finds such one person, talks to them, establishes a relationship, gains their trust, and from them starts contacting other people and learning about the relationships among them, and sort of builds out from there via some sort of breadth first search like process. If this is the process by which your data is generated, then you have to be a little careful about the interpretation of what happens when this person is present or absent from the data set. Because what you're not necessarily hiding is like their participation in the study. So you can remove their data from the data set, but then just their mere presence in the data set actually dramatically changed the set of other nodes that were contacted. Okay. So the only sort of caveat I want to clarify about differential privacy in this type of context is you have to think about sort of the whole process and not only the kind of computation you're doing at the end to analyze the data. So you have to think about the whole thing, the privacy of the entire process. And that's something that's reasonably complicated to do and something we don't necessarily always have a good handle on. So I just want to sort of have that warning for you. Okay. With that, but that caveat being explained, I'd like to then talk about, well, what kinds of things can we do, subject to this still pretty strong definition, which is node differential privacy. Yeah. That's entirely plausible. The question was, maybe in this sort of second setting, you can argue that if, depending on the kind of network it happens to be, maybe you can argue that the set of people you end up contacting is basically a random sample, except for the first few, and then you can sort of, basically you don't need to worry about, you can sort of assert that the influence of this seed on the final set is not very high. That may well be true, but again, that's going to be a sort of a situation-specific reasoning that you're going to have to do. Okay, so I guess I just want to say that, thinking about the correctly modeling privacy in this type of setting is a subtle point, and one that, deserves thought. But, that said, I'm now going to leave the modeling question behind and sort of launch into the algorithmic and computational techniques we know. Okay, so there were sort of a bunch of works on computing various things, interesting things about graphs subject to this strong guarantee. People looked at various basic counting statistics, so like just figuring out how many edges there are in the graph, or counts of small subgraphs, like for example, how many triangles or other structures occur. People have looked at algorithms for releasing the degree distribution. Sorry, these are pictures that go with this. And I'll mention this towards the end, a few other things. Ideally, what we want are algorithms for these statistics that are node differentially private for all graphs, but that are accurate for as large a subclass of graphs as possible. And as we'll see, it turns out we can't get accuracy, the type of accuracy we want, for all possible graphs. And so we're going to have to aim for some sort of relaxation of the notions of accuracy we want, and specifically we're going to kind of restrict the class of inputs for which we're going to be able to provide accurate answers. But we still want a privacy guarantee that works for all data sets, because we don't want to make too many assumptions about the data set that we can't go and try to verify. And then we're, for these types of statistics, we're going to look at, for sufficiently good approximations, and what type of approximation we can provide, I'll say more about later. Okay, so there are sort of, roughly speaking, two classes of techniques for these, for node private algorithms. One is sort of what are called sort of simple projection techniques. So I'll explain where those come from. Another are what are called Lipschitz extensions, and I'll explain what those are. But these are basically the two classes of approaches. One of them is sort of a very generic approach that gives us sort of a generic reduction to reasoning about privacy in a subclass of graphs that's a little easier to think about, namely those where there's a known upper bound on the degree of any vertex. And then the Lipschitz extension technique is more general. It yields more accurate algorithms, but it's limited to statistics that have some additional structure. And for example, things with like subgraph counts and the degree distribution of a graph. And then there's this sort of both of these techniques come with you have to choose a bunch of parameters that you have to tune. Like there's a bunch of knobs you have to tune on these algorithms to tell you exactly what kind of accuracy trade-offs you're going to get. And there's also sort of a technique for trying to select those parameters in privately as accurately as possible that I'll tell you a little bit about. Okay, so I'm going to mostly focus on Lipschitz extensions for this talk, and I will explain what they are and why we need them and all that now. Okay, so let's travel in time back to Sunday when we were learning about the Laplace mechanism, and we had an input and we wanted to compute some statistic f on this input. And so what we said is we wanted to do some kind of processing and release an approximation to f of g on the data, to f applied to the data. And in this case, the data is this graph. Okay? And we want to know how accurately we can do this subject to epsilon differential privacy. So recall that for the Laplace mechanism, the structure we were looking for in the function was global sensitivity. So this was the maximum over neighbors, g and g prime, of the difference between f of g and f of g prime in absolute value. Okay, and I'll note that delta f in this talk. Okay, so this is also some kind of Lipschitz constant about. Okay, and as we know, so this is we know that we can add Laplace mechanism, use the Laplace mechanism to add noise about delta f over epsilon. Okay, so let's look at a couple of functions and look at how sensitive they are to changes in the graph. Okay. So on one hand, we could look at the number of edges in the graph, and another function that we'll play with is the degree list, the list of degrees, the sorted list of degrees in the graph. Or alternatively, you can think about this as just like a degree histogram. You know, how many nodes there are of each degree in the graph. Okay, so how sensitive is, say, the number of edges in the graph to the insertion or removal of a vertex with an arbitrary set of edges? Well, I can, if I've got a graph of size n, I can add a new person that's connected to everybody else, and the number of edges in the graph will go up by n. Okay. And if I look at the list of degrees in the graph, and I think of it as a long vector, and I want to know its sensitivity in the L1 norm, then its sensitivity is also very high. It's also going to be sort of on the order of n, and that's because when I add a new vertex to the graph, not only do I create a vertex, like I add a new entry to the list whose magnitude is n, but I also change all the other degrees in the graph by 1. Right? So this whole vector gets shifted over, and a new entry gets added. Okay, so it's a fairly global change to the statistic, and so it's kind of hard to say that. I mean, you could try adding Laplace noise proportional to these quantities, but in general, it wouldn't work very well. Sorry, let me go back a second. So what is going to happen is that suppose that if my graph were somewhat sparse to begin with, like say it was a graph where the average degree was 6 or something like that, then adding noise on the order of n to the number of edges would essentially sort of destroy any information in that statistic, right? I wouldn't be able to distinguish between average degree 6 and average degree 4 or 5, right? Which is maybe something I actually really want to know. Yeah?
In the second example, before we add a new vertex, every vertex has a big even degree, and then we add a new vertex and edge to each of them, and generally almost all of them will be at an odd degree.
Yeah.
So does it mean that it can change in n square?
Oh, so yeah, so that's why I sort of phrased it as the list of actual degrees. So if you just think of a sorted list of degrees, each of these numbers changes by at most 1, and then there's a new entry that gets added to the list that is larger than that. Yeah, so if you the histogram thing that I mentioned is not is actually kind of a brittle representation. A more stable way to represent it is in terms of this list of degrees, and then you can transform that afterwards if you want. But, yeah. Okay, so what's going on in this example? The things that cause such high high sensitivity are exactly the possibility that we have to hide the presence or absence of even a single large degree vertex in this graph. Okay? And it's not that we can rule, I mean, depending on the setting, it's not that we can rule out the existence of such a vertex, right? For example, there could be one very well-connected person in the graph or a small number of very well-connected people in the graph. But if we are going to sort of give statistics using this global sensitivity framework, if we want to provide, satisfy our constraint of differential privacy, then we're going to have to be, via this type of mechanism, we're going to add a lot of noise in settings where the, a lot of noise sort of uniformly over all graphs, even on graphs where the statistic we're interested in computing is pretty small. Okay. Maybe I'll give you one more example to think about, which is the the number of triangles in the graph. And if you feel like it, you can think about what the global sensitivity of this statistic is in the context of under this sort of node notion of adjacency, and I'll come back to this example a little later in the talk. Okay, so okay, so we said on this slide that the problem is that we might have some high degree vertices in the graph, and if there are some vertices whose degree is much larger than, say, the average degree, then we're going to start getting problems in terms of sensitivity, and or the fact that we have to sort of defend against such vertices is causing problems. Okay. So instead, we'd like to somehow focus on graphs where there are no such vertices without sacrificing our overall privacy guarantee. So for some notation, let G be the family of all graphs, and G sub D be the family of graphs whose degree on all vertices is bounded by some parameter d. And d need not be like a constant. It could be square root of n or something large, but it's some parameter, and eventually we're actually going to want to choose that parameter relatively carefully. So we're going to consider two notions of sensitivity. One is the notion we had a second ago, which is the global sensitivity over the entire family of graphs. And the other is sort of some notion of sensitivity restricted to the family of graphs of degree at most g. Okay? And this is really just the maximum over pairs of graphs in this family that are adjacent, and which of how much the function can vary over graphs in the family. Okay? And the observation is that when we restrict ourselves to this class, then we get much lower sensitivity for a lot of natural functions we'd want to release. So for example, if I just look at the number of edges in the graph, suddenly my sensitivity drops down to about d instead of about n. Okay? And if we wanted, again, the sensitivity of the degree list, it drops down to about 2d instead of about 2n. Well, exactly 2d instead of exactly 2n. And so, inspired by this, it would be nice to get, it would be nice if we could somehow get privacy for all graphs, and yet add noise proportional to this sort of more restricted notion of sensitivity on those graphs which lie in this subset or are close to this subset. Okay, so we'd like to get error comparable to this more restricted notion without losing our privacy guarantee. Okay. And yeah. Okay, so the question is, can you sort of get away with somehow considering decomposing the graph into a collection of subgraphs such that the original graph is the union of edge sets of these subgraphs, and separately release statistics about each of the subgraphs, And I mean, the issue is how the sort of straightforward ways of doing that decomposition, you're going to pick up a lot of noise from the fact that you're releasing separate information about each of these things. Arguably, you can think about what I'm going to present as doing this in some not exactly explicit way. Okay. So the first idea we're going to look at is to use what's called an extension. Okay? And so what this means is we're going to take the function as defined on this small set, and we're going to kind of extend its definition to the entire set of graphs in such a way that the value of the function may be changed greatly for graphs that are far away from the set, but it'll remain the same for graphs that lie in the set, and it'll remain close for graphs that are somewhat nearby. Okay, so we say a function f prime is a Lipschitz extension of f from GD to G if f prime agrees with f on G, and outside of G, we don't require that the functions agree, we just require that f prime be have low sensitivity everywhere. So f prime is sort of a smoothed out version of f, which agrees with f on the set we care about, and may or may not agree outside that set. Okay. Now, once we have this kind of thing, we can release, instead of releasing f, we can release f prime via this global sensitivity framework. And so that'll allow us to get, privacy for all possible graphs and accuracy on those graphs that sort of satisfy the assumptions we're making, lie in this set. We don't need to only look at extensions from the sets of graphs of degree at most d. There are other sort of natural sets of graphs that we might want to use, and I'll give you an example or two later, but let's just play with this example first. Okay, so the next question, of course, would be, well, when do such Lipschitz extensions exist? Like, when can you actually do this? And it's been known for many, many years in the functional analysis literature that if f takes values just on the real line, if it's like a one-dimensional statistic, then it will always have a Lipschitz extension. So this is sort of a very general result that works for all sorts of different metric spaces, but in particular it applies here. What one of these papers that worked on this problem, in fact, a couple of these papers, I'm citing ours here, but there's like another paper of Chen and Zhou that also provided this result implicitly and independently around the same time. We gave Lipschitz extensions for a certain class of functions that are not only, we know they exist, but these extensions have the additional property that they can be computed efficiently, that they can be computed in polynomial time. They're relatively simple algorithmically. Okay. Whoa, something weird happened to my slide. Whoa, okay. Somehow, like the animation somehow got messed up. Okay, well, let me, okay. So for vector-valued functions, the picture is more complicated. And for vector-valued functions, we don't always have a nice Lipschitz extension. So in order to sort of capture what's going on, we're going to need a notion of how good an extension we can get. So we're going to introduce an additional parameter, which is the stretch of the extension. And the stretch of an extension is a number, a sort of a multiplier in front of the sensitivity. So we want a function that agrees with f on the entire graph, and such that its sensitivity outside, not on the entire graph, but on the set we care about, and its sensitivity outside this nice set is not too high, is bounded by some small, hopefully small multiple of the sensitivity on the smaller set. Okay? So if we have such an extension, we can still release the value of f prime via the usual Laplace noise framework, and now we'll just be paying an extra factor of s in the amount of noise we add, and so as long as s is not too big, this is not a reasonable thing to do. Okay, so So stretch 1 Lipschitz extensions, it turns out, don't always exist. It's not hard to construct an example of a function, let's say, that maps into R3, so it's just a vector of length 3, who's such that all of its extensions are, their stretch is bounded below by some constant that is larger than 1. I forget what the exact constant is in the result. It's like 1.5 or something like that. Okay, so we don't know sort of a general, there's not a very good general result on when nice Lipschitz extensions, like the functions for which nice Lipschitz extensions do or do not exist. And for all we know, it could be the case that every vector valued function in this particular metric space of bounded degree graphs has an extension, a Lipschitz extension with, say, constant stretch to the entire set of all graphs. So we don't know whether or not that's the case. We don't know if they all do or don't. But what we do know is we have like extensions of, relatively simple extensions of a couple of high degree sort of summaries of a graph, and in particular the degree list and the degree distribution, which is closely related. So these can be extended with small stretch in a way that can be computed efficiently. Okay, so in general, even the existence question is open, whether or not there always exists an extension with small stretch, and the question of computational efficiency is, even more open, whatever that means. Okay, so let me explain. Let me give you an example of a Lipschitz extension for the number of edges in the graph. So this is a nice simple function. So again, we're counting the number of edges in the graph, and the problem is that if we add a new node to the graph and add with lots of edges, then the number of edges can jump up significantly. So what we want to do is somehow smooth out this function in such a way that when the number of edges when all the vertices in the graph have relatively few edges coming out of them, we get exactly the number of edges. But when there are a small number of high degree, or when there are any high degree vertices that get added, they don't cause our proxy for the number of edges to jump up suddenly. Okay, and there are like a couple of the natural things you would try. The first thing you would try is just to sort of throw out high degree vertices and report the number of vertices among the remaining vertices in the graph. And it turns out that particular approach doesn't work here. But here's like a relatively simple thing that does. So suppose I'm given a graph G, I'm going to define some flow. I'm going to reduce this to a network flow problem. So I'm going to define a flow instance as follows. I'm going to create 2 copies of every vertex in G. Okay? So I'm going to take, if my graph originally had 5 vertices, I'm going to have on the left 1 vertex for every original vertex, and on the right another vertex for every original vertex. And I'll connect these copies in a way reflecting the original graph. So vertex 2, if it was connected to vertices 1, 3, and 5 in the original graph, it'll now be connected to vertices 1, 3 prime, and 5 prime. And we're going to orient all the edges so they go from left to right. So sorry, given that this talk is in Israel, maybe I should have gone the other way. Right. So we're going to we're now going to create 2 additional vertices, a source vertex and a sink vertex. And I'm simply going to put edges from the source vertex to all the left vertices, edges from all the right vertices to the sink. And I'm going to put capacities of D on each of these edges. Okay, so the edges in between, in the middle of the graph, are all going to have capacity 1, and the edges coming out of S are going to have capacity D, and the edges going into T are going to have capacity D. So the only place where the degree bound is coming in is exactly in the capacities of the edges coming out of S and T. Okay? So if you're not used to flow problems, just a sort of a metaphor for thinking about what's going on, we're designing a graph, we've got edges, we're going to imagine that each of these edges is a pipe, and the capacity the capacity of the edge is sort of the cross section of the pipe. And what we, so like how much water can flow through the pipe per second at a given pressure. And what we're going to ask is, like, if we were to hook a pump up to vertex S and let water flow through the network, how fast would it come out at the other end of the network, at the sink? Okay, and if you think about it for a minute, I mean, I don't know how many people have seen flow algorithms in classes before, but this physical intuition is actually a pretty good intuition for how to solve this problem algorithmically. And there are a variety of algorithms for solving flow problems reasonably efficiently. Okay, so we're going to look at the value of the maximum flow in this graph, okay, what we'll call V flow. And the claim is that if I take V flow and divide that number by 2, then it is a Lipschitz extension of the number of edges from the set of graphs of bounded degree to the set of all possible graphs. So let's just like step through that reasoning. Well, what do we need to prove? The first thing we need to prove is that if the graph has if the graph really has degree at most d in all its vertices, then the value of the flow is exactly twice the number of edges in the graph. And the second thing that we want to show is that the the value of the flow can change when we add or delete a vertex in the graph is at most twice the sensitivity, this restricted notion of sensitivity of the number of edges, which happens to be d in this case. Okay, so let's do the first. Okay, great. Make sure I'm got the right animations for the right proof. Okay, good. So let's prove the first statement. So remember, so if we sort of look at how much flow can get out of vertex 1, so it's got d units of flow, the pipe going to 1 can carry d units of flow, but there are only 2 pipes leaving vertex 1, and each of those has capacity 1. Okay? So I can never route more than 2 units of flow through vertex 1. Okay? So in fact, I might as well imagine that the capacity along that edge is exactly the degree of vertex 1 when we're in the setting where the degrees are all bounded by d. Okay? So I'm going to imagine what I'm going to do is I'm going to start with S. I'm going to push degree of V units of flow from S to each vertex V. I'm going to push as much flow as I can across the middle part of the network. I'm just going to use every single pipe to its full capacity. And then at the other end, again, if I look at if my original, sorry, this is the picture corresponds to an undirected graph. It works for a directed graph too, but it doesn't matter. If I look at the flow coming into 1 prime, it's got 2 units of flow coming in, and so I can get 2 units of flow going from 1 prime to t. And so what I can do is I can construct a valid flow for this graph where the value of the flow is exactly the sum of the degrees in the graph. Okay, so when all the degrees are bounded by d, the value of the flow is exactly the sum of the degrees, and the sum of the degrees is exactly the number of edges. Okay, is exactly twice the number of edges. All right. So this shows you that the value of the flow is the value of the maximum flow is at least the thing we want, and it's kind of easy to see it can't be any better because the cut that goes right down the middle of the graph is saturated in this example. Okay, and now if I want to know why the flow can't change very much when I add a new vertex, well, let's add a new vertex and see what happens, right? So we'll add vertex 6, and now when we go to construct the new flow graph for this new graph G prime, I'll get 2 additional edges from S to 6 and 6 prime to S, and then whatever additional edges vertex 6 brought to the graph. And now I want to argue that this this new graph, the new flow won't be any higher than 2D, won't be more than 2D times what it was before. And the first thing to observe is that the value of the flow can only go up because I'm adding edges to the graph. So I'm just making it easier for water to get from S to T. And then I can sort of account for this is like a picture of a cut, but it doesn't really matter. I can account for any new flow from S to any new units of flow from S to T. I can either charge them to units of flow leaving leaving S to go to vertex 6, or leaving 6' to go to T. And so the new new units of flow passing from S to T are bounded. The number of new units is bounded by 2D. So, so what's going on in general here is that I'm sort of using the flow going from S to each of these vertices. I'm using it as sort of a soft proxy for the degree of the vertex. So if all the degrees are at most d, then the flow going from S to a given vertex is exactly its degree. And in general, as I start adding vertices to the graph, then these flows will start changing, and they may not achieve the degree. They may be less than that. They may not even achieve the minimum of d in the degree. But there's some sort of not too quickly changing value. Okay. Somehow I'm missing one of the slides I expected to be here. So I'm wondering if I'm using the wrong version of the talk. I'm sorry. So this is not exactly the version I wanted to work with, which is not a big deal, but there was one slide that I'd added that somehow got lost. Okay. So I'll do the thing I wanted to do on the board in a second. Okay. So let's just talk about. So this is very simple. This is just the number of edges in the graph. But we really want to do sort of more interesting descriptive statistics about the graph. One, pretty basic quantity that we might want to be able to do is the degree list. And this whole flow framework for thinking about it can be generalized to that problem. You can sort of measure the, you could take this flow network, and for every vertex in the graph, consider the flow, look at the maximum flow, and look at the flow going from S to that vertex, and call that, the sort of soft degree of the vertex, and we could try to use that as a proxy for the degree of the vertex, and rather than giving the sort of degree list, we could imagine outputting the list of these soft degrees, okay, which again would be the same as the degree list when the maximum degree is bounded. Okay, the problem with this approach is that the true maximum flow is not unique. It could be that there are, the value of the maximum flow, there's a unique sort of amount of water we can pump through the system, but it could be that for a given graph, there are different ways of achieving that maximum. And so these sort of flows may not be well defined, and they could sort of jump around in weird ways when I start changing the graph. And so what we want is to sort of make the flow unique, make it well defined in a way that preserves, that sort of changes smoothly as we change the graph, so that keeps this sort of global sensitivity guarantee. And it turns out that one of the way to do this is that instead of maximizing the total amount of flow that's coming out of the graph, the vertex S, what we'll do is maximize some function of these flow some sum of functions of these soft degrees, where this function is sort of strictly concave. So one that works fine is this little quadratic function. Okay, so what we're looking at is, again, instead of maximizing the sum of the flows, we're maximizing the sum of, roughly d minus the flow squared. Okay. And what we can argue is that if I maximize this sort of concave function instead of the true flow, the sum of the flows, then in fact what I will get is I will still get a maximum flow. I'll still get the thing I kind of wanted before, but because of this concavity restriction, I'm optimizing a concave function, the maximizing flow is now unique, and you can argue that it doesn't actually change very quickly, that it is in fact a Lipschitz extension of the degree list with stretch 3/2. Okay. So after we gave this construction, someone else came along and sort of thought about it for a while and took. Before coming up with this construction, we tried a bunch of combinatorial constructions, none of which worked. But apparently we didn't try them all because someone else came along and came up with a much simpler one, which I'll also explain. So just recently, so that the construction I gave you was from about 3 years ago, even though it only appeared in print relatively recently. But then very recently, Day, Li, and Liu at Sigmod, sorry, there's no N there, gave a kind of a completely combinatorial version of this, where what you're going to do is start with an empty graph. And what you're going to do is just come up with some ordering of the vertices in the graph, so let's say lexicographic. And now what you're just going to do is try to start with an empty graph and add the edges in to this empty graph, and just ignore edges whose addition would violate the basic degree constraint. Okay. And it turns out that this process, when you're done, if you then compute the degree list of whatever you got, the subgraph that you got in this manner, and sort the list of degrees, then you will get the sorted degree list will have low sensitivity. Okay? And actually the insight that we were missing when we thought about this is it's actually the sorting operation is required to get low sensitivity here. This is somewhat surprising, but it's not a very hard argument. Once you know what you want to prove, it's easy to prove. But it's a very cute, simple algorithm, and it actually gives us not exactly a perfect stretch. It's not stretch 1, but the sensitivity is basically the same as before. It goes up by at most 1. Okay. So this is another way of getting. This is in this case sort of a combinatorial way to get the thing we want. And I should mention, to use these extensions of the degree list, you need some additional ideas. So, for example, if you use our construction or the other construction, you compute some sorted degree list in their case, or these flows in our case. You add noise, Laplace noise to, you sort the resulting vector, add Laplace noise to each coordinate, and then in order to get anything that's actually useful, you then have to do some kind of post-processing on this sorted vector to kind of decrease the amount of noise. And the reason you can do that is because the original vector is sorted. And so because you know the original vector is sorted, you can dramatically reduce the amount of noise that you actually add, and that makes a big difference in this setting. Okay, so it's not enough just to sort of, for these higher dimensional structures, it's not enough just to have an extension. You also need to think about how exactly you're going to use it algorithmically afterwards. Okay, so what time am I supposed to stop this session? How much time do I have left? Am I 3:15 or? Okay, all right, good. Okay, so. Just to give you another idea of the kinds of things we can do, it turns out this sort of the general approach I gave to sort of taking the releasing the number of edges and coming up with an extension to the number of edges in the graph also works for other kinds of statistics. And the general philosophy is what we'll do is we'll write some, so let me go back to the original flow graph picture I had. Okay, and so let's just sort of think more abstractly about what was going on here. We took the problem we kind of wanted to solve. In this case, it was like figuring out the degrees of the vertices or the sum of the degrees of the vertices. And we expressed it as some kind of optimization problem over continuous variables. And then we constrain that optimization problem in a specific way that would allow us to bound the sensitivity, to keep it from jumping around too much. Okay? And it turns out that sort of general way of thinking about it applies to lots of other problems. Okay, so let's, for example, take the number of triangles in the graph, which I'll call f delta. So, so let's start by coming up with a really complicated way of counting triangles. And then we'll change it, right? So what I'm going to do is I'm going to define a variable. I'm going to define a linear program. And it's going to have the variables of this LP. It's going to have one variable one variable xt, which is bounded between 0 and 1 for every triangle in the graph. Okay, so notice in particular that the set of variables depends on set of variable depends on the edge set of the graph. It depends on the graph. And it's going to have, and the constraints, well, we're not going to introduce any constraints quite yet, but we will, other than the fact that the variables are bounded. And then the optimization function, the objective function that we want to optimize, is we're going to try to maximize the sum over triangles that are actually in the graph of these variables. Okay. So this is not a very interesting linear program. There's nothing that's relating the variables, and so if I want to maximize the sum of the random variables, of the variables in this linear program, I basically just assign a 1 to all of these x's, and then the value of this linear program will be exactly the number of triangles in the graph. Okay, so that's not a very interesting way to count triangles. Notice I still have to count the triangles to set up this linear program. Okay, so now what we're going to do is for every vertex v we're going to add a constraint, which is going to be that the sum of the triangles, the sum over the triangles that contain the vertex of x sub t is going to be at most this some number d. And actually, I'm not going to call it d. I'll call it lambda. Okay, so it's some bound that we'll set in a second. Okay. All right, so now I've got non-trivial constraints on my linear program, and so solving this is some packing linear program which I can solve using a variety of different algorithms. It's relatively efficient to solve these specific kinds of programs, and so I'll get some number, and notice that the value of the linear program has the value of this linear program is the thing I'm going to output. And so the first thing to notice is that if no vertex participates in more than lambda triangles, then the value of this linear program is equal to the number of triangles. Okay? Because basically, if no vertex participates in more than lambda triangles, then these constraints will never be binding constraints. I mean, they could be tight, but they're not going to limit the object. They could be tight if there's exactly lambda triangles, but they're not going to limit the optimum. Okay. On the other hand, sort of for any two graphs, if I take some graph, if we now add, regardless of whether or not this lambda constraint was satisfied in G, if we add a new vertex, let's call it U to the graph, with a bunch of edges, then how is this linear program going to change? Well, what I'm going to do is I'm going to get a bunch of new new variables for the new triangles that were introduced by the vertex and its edges. However many those are. So I get some new number, and I get some new constraint, which is that the sum over these new triangles is at most lambda. So when I change the graph, I'm introducing a bunch of new variables and one new constraint. But that new constraint only constrains the new variables. Okay? So that means that any solution to the previous linear program remains a solution to the new linear program, so that the value can only go up. And secondly, the amount by which it can go up is bounded by lambda, because any solution to the new linear program can be transformed into a solution to the original by just removing these variables. Okay? And so what we can say is that the value of this linear program on the two graphs will differ by at most lambda. Okay? And so we get like a nice sort of smooth extension of the number of triangles, and it's not too painful to compute. It's not ideal, like you still have to enumerate all the triangles and solve this linear program, but it's something that is feasibly can be done, and we had an undergraduate at Penn State actually implement this, and it wasn't the end of the world. It ran in very reasonable amounts of time. Okay, so this is just to give you an example of like the kinds of flexibility one has in sort of designing these types of extensions. It's kind of smoothing things out. And there are various interesting questions in terms of computational efficiency. So for subgraph counts, this general framework will apply, but then for other types of functions, it's less clear you can get these things, and there are various open questions that I can tell you about if you're curious. Sorry? Oh, sorry, why do I care that it's triangles? Oh, no, yeah, I don't. I mean, this will work for any class of, like, any kind of counting problem where you're counting local structures. Okay, also, one thing I didn't mention is if you think on like, for example, if I give you a particular graph, a specific graph, and I ask you, by how much could you change the number of triangles in that graph? Let's say by deleting a vertex. Then the maximum amount by which you could change it by deleting a vertex is exactly the largest number of triangles that are involved in any one vertex. And so there's this sort of, so basically there's like a sense in which this guarantee on when the extension matches the number of triangles is as tight as possible. There's sort of like some tightness statement hiding in here that I'm not going to sort of formulate explicitly. Okay, let me sort of jump forward and wind up. Okay, so I'm not going to go through the details here. I'll just finish quickly. So given some like real valued Lipschitz extension and so let's say I'm back to looking at releasing some function, and I want to sort of think about releasing it on graphs of a certain bounded degree. What I can do is basically for a given function, I get like a bunch of different extensions, one for every value of d. Okay, and these extensions have sensitivities, a different one for each extension. But basically, that sensitivity will increase as d increases, because I'm giving it like more pairs of graphs that it has to bound. And so if we are to like use this thing to add noise, as I said we could do, then the final error we're going to get in our overall algorithm is actually a sum of two terms, right? On one hand, it's the difference between the value of the true function and the value of the extension. And this difference is going to be non-zero when when this number little d is actually less than the maximum degree in the graph. And then there's this sensitivity, which is the sensitivity, the sensitivity term due to adding noise. Okay. And so what we really want to do is, we don't necessarily know what the right value of d is ahead of time, right? So the right value of d in particular need not be the maximum degree in the graph. In fact, generally the right value of d is much smaller than the maximum degree in the graph. And so what we really want to do is kind of privately select the right value of d to help us release this function. And so we're going to try, we've got some other optimization problem that we want to first solve privately, which is choosing the best value of d. Okay? And it turns out that this doesn't sort of fall very neatly into the usual framework for the exponential mechanism. And the problem is that these score functions, which are the errors I would get for different values of d, they themselves have very different sensitivities. Roughly speaking, the score function is going to have sensitivity, something like on the order of d, okay, or it'll change with d. Okay. And so I get this sort of weird minimization problem where I'm trying to select a bunch among a bunch of scores, but with very different sensitivities. And so the usual exponential mechanism won't work well, but it turns out there's like a different thing you can do, and I'm not going to go through it because I'm like running out of time. Okay, so so just to conclude, it's possible to design no differentially private algorithms with good utility for a large class of graphs. And I didn't really explain how you do it, but it is in fact possible to choose a good value of d privately of these sort of not necessarily of d, but in this case of lambda, it's the same story. Okay, so there are various directions that are open here. So unlike many of the other topics we've been discussing in the lectures today, here things are much less well understood. We don't really know which functions have efficiently computable Lipschitz extensions. There are lots of things we'd like to do with graphs, such as when we're trying to release many different statistics, and we'd like some version of the private multiplicative weights algorithm that we don't really know how to do anything interesting there with graphs. We'd like to generate nice synthetic graphs, which is sort of a non-trivial problem that there's been some work on, but not much. And just to give you a very concrete open problem, is there a no differentially private algorithm for releasing the cost of all possible graph cuts so this is where I want to release a structure that allows me to figure out how many edges cross any particular cut in a graph with worst case error strictly less than n times the maximum degree in the graph. Okay, so n times the maximum degree in the graph is sort of a more or less a trivial bound, and but beating that is not we basically don't know how to do it. It's an open problem. All right, I'll stop there. Thanks.